Time series prediction of temperature in Pune using seasonal Arima model. Abstract, an effort has been made to develop a SARIMA, seasonal autoregressive integrated moving average, model for temperature prediction using historical data from Pune, Maharashtra. The historical dataset from the year 2009 to 2020 has been taken for observation. When there is a repeating cycle is present in a time series, instead of decomposing it manually to fit an Arima model, another very popular method is to use the seasonal autoregressive integrated moving average, SARIMA, model. Time series currently is becoming very popular, a reason for that is declining hardware's cost and capability of processing. The model can be used to set the outline for the upcoming year. Enumerate the effects of unexpected changes or disruptions in the system. The seasonal Arima model is designed by running Python 3.7.4 on Anaconda Jupyter Notebook and using the package matplotlib 3.2.1 for data visualization. The goodness of fit of the model was verified against standardized residuals, the autocorrelation function, and the partial autocorrelation function. We discover that SARIMA, 1,1,1, 1,1,1, 12 can represent very well in the performance. We found MA of 0.60850 and RMSE of 0.76233 for SARIMA model. According to the model diagnostics, the model was good for predicting temperature. Keywords SARIMA, prediction, Arima, temperature. Introduction. The primary aim of time series model is to accumulate and take a look at historic values to develop suitable models that describe the essential structure and traits of the time series. Alternatively, the time series forecasting model observes distinct values and expecting to predict future values. Regression evaluation method often tests theories that the current data of one or more time series has the impact at the present data of another time series one. Time series statistics occurs in lots of areas like economic analysis, sensor monitoring of community, evaluation of scientific issues, and mining of social interest. Greater recent fields focus on the subject and talk to it as time series forecasting. Forecasting contains taking models fitting on past data and using them to predict future remarks. Descriptive models can derive for the future, i.e. to smooth out or eliminate noise, they are just trying to better define the statistics. An important distinction in the forecasts is that the future is completely impossible to obtain and that one should expect only that which has already taken place. The prediction of time series is the use of a given model to predict future values against historical values, and can therefore be understood as a method. Separate numerical forecasts of meteorological forecasts and time series use a model to predict future values based on historical values. Owing to the position of time series forecasting in uncountable practical fields, researchers should pay attention to fitting a suitable model to the time series. Over the past many years, many intelligent time series models have been developed in the literature to improve the correctness and effectiveness of time series forecasting. One of the most widely used and known time series models of statistical forecasting is the Integrated Moving Average, ARIMA, self-regulatory model. The ARIMA model is well known for notable forecasting correctness and effectiveness in representing various types of time series 3 with simplicity as well as the associated, Box-Jenkins's methodology for optimal model construction. For seasonal time series forecasting, Box-Jenkins 4 proposed a relatively effective variation of the ARIMA model called the seasonal ARIMA, SARIMA, model. The main design objectives for this paper are set out below. 2. Literature survey. Rios Moreno et al. 5 used outside air temperature, relative humidity, air velocity, and global solar radiation flux as outside variables to an autoregressive, AR, and an autoregressive moving average, ARMA, model. They effectively forecasted the room temperature in a university room in Mexico. The results showed that the outside variable older than 20 minutes did not recover the performance of the model. Felice et al. 6 used a non-seasonal time series method to predict energy demand at the national and regional level in Nigeria. It was established that using temperature as an outside variable enhanced the prediction results. Mahmudur Rahman, Ahm Saiful Islam, Sahamaknun Nadvi, Rashidar M. Rahman, 2013, examine the ARIMA and ANFI's model and outline how the model ARIMA can more efficiently capture the dynamic concert of properties, say weather, temperature, humidity, and air pressure, which must be compared by various evaluation measures, for example, with the mean square error, MSE, R-square error, and the sum of the square error, SSE. 7. And the author can check whether ARIMA would yield a more precise result than other models. In addition, 8 accepted the study to examine the trend and forecast the maximum monthly temperature in Nigeria using the SARIMA model. According to the simplest suitable SARIMA model, the predicted maximum temperature of 5 years is slightly stable compared to that of reference. In another review, 9 fitted SARIMA model to average temperature for the measure of 1980 to 2010 of Debrugger utilizing automatic Arima function, i.e., Autoregressive, in our software. Keeping these points in mind, an effort has been made to develop a SARIMA model. 3. Methodology. Temperature data recorded from 2009 to 2020 were obtained for Pune city, from the Meteorology Department at 1-hour intervals 12. The longitude and latitude of the automatic weather station is 73.856255 and 18.516726, respectively. The data collected has different parameters, such as date time, temperature, humidity, moonrise, wind speed, wind direction, pressure. From this, we have eliminated features that have large amounts of missing data, and we have considered temperature as an input parameter. The seasonal Arima model is implemented by running Python 3.7.4 on Jupyter Notebook and using the package matplotlib 3.2.1 for data visualization. Time series plot of temperature for the year 2018 was shown in Figure 1. The hourly temperature data during 2009 to 2018 is used as the training set, while that during 2019-2020 is used as the testing set. To evaluate the forecast accuracy, as well as to compare the results obtained from different models, the mean square error, MSE, is calculated. Check Stationerity. If the time series is not stationary, it needs to be stationarized through differencing. We tested our dataset Stationerity by augmented Dickey-Fuller test and found that it is not stationary. Take the first difference then, determining stationarity with an augmented Dickey-Fuller test until p-value is less than or equal to 0.05, p equals 0.05. The order of differencing D is chosen such that it minimizes the standard deviation. The previously differenced series, which is now a stationary series, might still have some autocorrelated faults which can be detached by adding AR terms, P equals 1, and MA terms, Q equals 1, in the forecasting equivalence. B. Plot ACF and PACF. In this step, the ACF and PACF of the data are plotted. Autocorrelation functions, ACF, and partial autocorrelation functions, PACF, are used to identify potential models. We can see there is gradual decreasing pattern in ACF plot while there is PACF cuts immediately after lag. Thus, the graph suggests that AR1 would be appropriate for the model. If there's a pointy cutoff within the PACF of the difference series and therefore the series shows mild underdifferencing, an AR term is added to the model. If there is a high limit in the ACF of the difference series and the series shows mild overdifferenced, an MA term is further added to the model. Then select the optimal model based on a performance metric like AIC, Akaika information criteria.